case where there is a pulley of some mass and moment of inertia of this pulley about this axis is 15 kilogram meter square and its radius is given as 1 meter. A string is wound over it and over here 10 kg mass is hanging. Initially the whole system is stationary and then this block is released and strikes the floor with some velocity. We are asked with what velocity this is going to strike the floor. One thing to notice over here is whenever the mass of the pulley is given, then the question belongs to rotational mechanics. The concepts of rotational mechanics will be used because so far when we had been doing the Newton's laws of motion, all the time the pulleys, they were massless, they were frictionless. Over here also at the axle, there is no friction, but now the pulley has got some mass. Instead of giving the mass, they have directly given as IO as 15 kilogram meter square, because that will solve the purpose. We can proceed with this. Now in this question, we see that there are two kinds of motion. This block has a linear motion, whereas this has a pure rotation. Pulley can only have pure rotation. And then there is some link between these two. This motion and this motion will come to that. So first, let's say this has a linear motion. So let's work as we have been doing in Newton's laws of motion. We have taken G as 10 meter per second square. So weight is 100 Newton, 10 into G. So translation equation for this is 100 minus T, that is 100 minus T is the net force. We are using net force is equal to mass into acceleration. We are using this for this block is equal to 10 into A, right? And for this pulley, T is here in this direction. And as F is equal to ma, similarly we use torque is equal to I alpha. And over here we have to remember one thing, that is when we say torque is equal to I alpha, we cannot change the axis midway. Whatsoever torque we are finding about one axis, we have to take the moment of inertia about the same axis and we shall be getting the alpha about the same axis. Torque is equal to Y alpha, and torque is also, we know, it is force into perpendicular distance between line of force and axis rotation. Over here, what is the force? That is, if we just look at this pulley, so force is this T and this is tangent. This string is always tangent to this. So this string is always tangent to this pulley. So T into R, that is 1, that is torque, force into perpendicular distance between line of force and axis rotation, is also equal to I into alpha. What we are doing? We are finding the torque about O only. Over here, we have a net torque. We are going to have a net alpha also. So for this body, about O, we find that is torque is T into R. R is 1 meter. So that is torque is equal to I. I about O, that is going to be 15 kilogram meter square into alpha. We don't know. So now we have this equation is a linear equation and this is a rotational equation. Is there something that is a connection between these two? Now we have unknowns like T, A and alpha. We have 3 unknowns, but we have just 2 equations. We know that is if we wish to find the value of T, A and alpha, then we need to have one more equation. The number of variables and number of equations, they should match. They should be same. Then only we can solve it. Over here, we see that is whatsoever the acceleration of this block over here, the same is of this, the same is of this, the same is of this, the same is linear acceleration of this point also, which is situated at the periphery also. And this, at this moment, whatsoever the acceleration is of this, the same is acceleration of this. But this point is at the periphery, it is also in circular motion also at this moment. So we can use A is equal to R alpha is very much applicable because this point has tangential acceleration as A. Linear acceleration of from here to here is everything is going to have same linear acceleration, and this point linear acceleration is also A. So A is equal to R alpha. So A is equal to 1 into alpha because R is equal to 1 meter. So with third equation, that is we get it as A is equal to 1 alpha. So we have 3 equations, we have 3 unknowns. From here we can get the value of A. Once we get the value of A, let's find out what is the value of A. So 100 minus T is equal to 10 into A. Over here, that is T into 1 is equal to 15 into alpha. Alpha is what? Alpha is A by 1. So we can put it like this. So these 2 equations we have. So if we add the two, 100 is equal to 25 into A, minus T plus T will get cancelled. So A is equal to 4 meter per second square. So acceleration of this is 4 meter per second square. Then after this, as usual, we can use the equation of kinematics. we can use the equation v square minus u square is equal to 2as. Over here we are starting our observation and over here we are closing our observation. So let's take it from A to B. V is the velocity at the final point of observation, that is at B, which is to be found out. U is the initial velocity at the point A. It has been released from rest, so U is equal to 0. 2, A is we have found out 4, S is 2. So V comes out to be 4 meter per second. So V comes out to be 4 meter per second. Is there any way that is we can solve this using the principle of conservation of mechanical energy? And we have done number of cases when we have done this conservation of mechanical energy principle in the chapter work, energy and power. So I would suggest you that is first you can go to that lecture, visit that lecture and understand. If there is any confusion, you can once again revisit that lecture and understand that is how we apply conservation of mechanical energy principle. And once you are thorough with the application, then you can come back to this chapter and proceed. Otherwise, here also I have simplified the things and you can continue if you wish.